Good morning, and in continuation in our final session, coming to you from the Springhill Marriott at the Newark International Airport, suite 511. Yours truly, Dolphy Gilpin, your instructor, and I promise us to do a mesh analysis in my final session. And here's it, and I hope that the video time will allow us. So here's it. So we have the mesh circuit now. And we call this mesh 1. This is mesh 2. And we assign for this voltage here a value of 15 volts, and VB a value of 10 volts. This resistance R1, you assign a value of the polarity plus minus, and this is the direction of the current going from positive to negative. And R1 is equal to 4 ohms. R2, which is this, current is coming so in this mesh, and it's going so in this mesh, and R2 is equal to 3 ohms. And R3 now is equal to 2 ohms. And for this, the current is assumed going in this direction. This is mesh 2. Okay. So what happened here now? We're gonna apply KVL to mesh 1 and mesh 2 to solve this mesh problem. So we say VA is 58 volts, R1 is 4 volts, and R2 is a that. So if we assume now that this point is A, B, C, D, E, and F, then going around mesh 1 in the direction now A, B, C, D, and back to A, that is so, and then the current is flowing in that direction. If we apply KVL, we're going to apply now Kirchhoff voltage law. We say now that VA which is a positive because it assumes the source voltage is equal now to let's say the sum of the voltage around a closed loop is equal to 0. So VA is positive, and there's a voltage drop across R1, which is equal now to minus now I1 R1 minus I1 R2, and now plus I2 R2, and that must be equal to 0. That's applying Kirchhoff voltage law. The sum of the voltage around a closed loop must be equal to 0, or that the sum of the voltage rises must be equal to the sum of the voltage drop. The drop voltages are considered the voltages across a resistance, and the rise voltage is a source voltage. So this is the equation now. But we know that VA is equal to 58. So we could say now that and I1 is common here,